we learn different solution model. So the very first solution model we learned was the random mixing model, the one lattice random mixing model. Okay, FCC solution or alpha magnesium solution, something like this. And then we moved to the compound energy. We moved to the Koji-chemical solution. And the Koji-chemical solution can be used both solid state as well as liquid state. One of the big difference of the Koji-chemical solution is the entropy of the Koji-chemical solution model is changing automatically with the interaction parameter between the A, B. Yeah, so the bonding actually energy in the solution can change the entropy. So that was the advantage of the Koji-chemical model. But it makes really big complexity in the entropy term. But anyway, that's actually big advantage. And also when we defined Koji-chemical model, we defined the coordination number. Okay. So for example, the FCC solution, theoretically we have to use coordination 12 because the nearest neighbor atom in the FCC is the 12. Yeah. And so that's why actually we have to use the coordination number 12. And the last time we also, I show you actually the coordination number in the liquid magnesium and the tin alloys. So liquid solution in the metallic solution. Typically, theoretical, actually the coordination number in the liquid alloys is about 10. So it's between the BCC and FCC, more or less. And however, in the fact stage, we are typically using coordination number 6 for the pure end member, pure metallic end member in the liquid solution. And then also I told you that one of the advantage of the modified Koji-chemical model, model 98, is we can realize the random mixing model inside of the Koji-chemical solution model. Okay, so we assume that the entropy is not changing depending on the interaction inside the model 98, and then we can realize those kinds of actually the condition in the Koji-chemical model. And we tried to actually make this solution last time, but we could not finish it. And when we tried this silicon tin binary liquid alloys, do you remember silicon tin binary system we tried last time? And then I say that we have to divide actually the L value by the Z number, so coordination number. So Z was the 6. And then we have to enter that number into the Koji-chemical parameter, in the actual random mixing parameter in the Koji-chemical model. Then you can get actually same result as a random mixing model. Do you recall this one? Do you recall this? And but when we tried that, it was not working. And I'm actually sorry. I forgot actually the some actually parameter there. And the real actually the equation you need is this one. So this is modified Koji-chemical model. Addition of random mixing inside the modified Koji-chemical model is like this. So there's some actually the explanation here. But so for example, in the Koji-chemical model, we assume that 2 moles of AB formation energy as delta Ag. Okay. But in the random mixing model, we assume half mole and half mole of AA, BB become 1 mole of AB as a regular solution parameter. Okay, so there's the factor of the 2 actually multiplied here. So in the end, I mean for the long story too short, in the end, when you have L parameter in the random mixing model, okay, and if you want to convert that L parameter to the Koji-chemical random mixing parameter, you have to do this way. So you have to multiply L by 2, and then you have to divide by the Z number. So for example, in the last time silicon and the tin, L parameter was given, L0, L1, L2 was given. And then each of these L, you have to multiply 2, and then divide by Z of the end member. So Z was 6 for the silicon and the tin. Then if you do that, you can get the new L parameter or new AB parameter, which you need in the Koji-chemical model. Okay, and you have to enter this number. So for example, so here, how we enter that kind of the Bragg-Williams model inside of the MQM model 98. So you have solution here, liquid solution is model 98. And then when you select the actual parameter, typically we add this last one for the chemical solution, okay, pair fraction. But instead of this one, you have to use this Bragg-Williams. You select the Bragg-Williams and then Nedley-Kister. Then internally, model 98 assume that this binary system is expressed as the random mixing model with a coordination number Z. Okay, so when you click this one, you can enter now L parameter, L0, L1, L2, L3, and this L parameter is same as, so this L parameter is original L parameter from random mixing model times 2 divided by Z. Okay, do you get it? So you have to divide by all the number in the previous L parameter by 3 basically, because 2 by 6. So it's by 3. You have to divide the L by 3. Then that's a new L parameter in the MQM model, considering the coordination number. And then you have to enter that number here. Then you're going to reproduce that parameter. Okay? Is it okay? So for example, before we do this, so let's stop sharing. And I'll open FactSage and then show you actually this example. Sorry. So let me share again. So this was actually the paper before. And by the way, I sent you the email yesterday, last night, and there was actually a mistake here. It was not the minus, it should be plus. Okay. So when you actually create the ternary solution for the MGSISN, you have to use this one as a plus. Okay. So in the homework number 2, you're going to do this one. And so you have to use this new actually the parameter here. So this L parameter here was the original L parameter in the random mixing model, assuming Z was 1. Z was 1. So one sublattice random mixing model without considering any Z. So it means Z equal to 1. So in order to actually realize this one, when you go to the solution, that was this one. No, sorry. What would be the one? SILC. I think this one. Yep. Here we have magnesium tin and then silicon. So when you click this one, this one, this one, and do the mouse right click and add the Bragg-Williams parameter and then Nedley-Kister type. Okay, this is what we are doing to realize this, the L parameter inside of the chemical model. And then when you enter that value, so for example, silicon and the tin here. So the first parameter, silicon and tin and Si. Tin and Si and tin. So L0 is same sign, so it's okay. So even you change actually this AB and power equal to 0, then it doesn't matter. Then this one is this divided by 3. Then this will be the value. Okay. And then second one, this one is this one positive, but because it's silicon tin and this is tin silicon, so you have to make minus first and then divide by 3. And then the last one again, so it's a L2 parameter, so the sequence doesn't matter. So it's a 4460 divided by 3, 1486. Okay, so you have to enter in this way. Is it okay? And then you can save it and then you can run the extrapolation, the calculation, then it will work. Okay? And then I show you already ternary interpolation technique in the liquid solution. So you can use that ternary interpolation to have the proper ternary the solution model here. Okay? Is it good? So now today, what we want to learn is this one. So now, what we want to learn today is model number 12 or model number 20. And this is so-called compound energy formalism. Okay. So I'll upload this file and after actually the end of this lecture. Okay. So compound energy formalism is nothing but it actually have the more than 2 sublattice. But each sublattice we assume that random mixing model. So it's kind of 1 sublattice random mixing model we learn, model number 1. And this is more than 1 sublattice random mixing model. So typically, when you have the more than 2 sublattice, we have to use this compound energy formalism. This is one of the most popular kinds of the formalism or model we are using for the solid solution. Okay, all the metallic system, all the ceramic system, typically we are using this one to describe actually the more than 2 sublattice crystal structure. Okay, and crystal structure, the solid solution. So for example, when you have this one, so let's look at it. Compound energy formalism is the formalism to represent complex solid solution structure using multiple sublattice model. Okay, and so for example, when you have this kind of FCC solution, iron, manganese, carbon, nickel, FCC solution. So iron and manganese is the substitutional element, and carbon and the nickel is the interstitial element in the FCC. So we have substitutional site and interstitial site. Okay. Theoretically, the number of substitutional site and the interstitial site is 1:3 ratio in the FCC. Okay. However, people already actually find out that among the 3 sublattice, in the interstitial site, 2 of them is always vacancy. So we don't have to worry about that one. So we only consider one of that actually the sublattice is only allowed for the mixing of some third element. Okay. So like interstitial element like carbon and nitrogen. Okay. So that's why we assume the substitutional and the interstitial, the ratio is 1:1 for the FCC solution. So it's based on the crystal structure data. Okay. So iron manganese going to the substitutional site, and carbon and vacancy was already originally in the interstitial site, but carbon and nitrogen can go together in the interstitial site. Okay. So then we have the 2 sublattice. And then the element here is the iron manganese, and element here is carbon, nitrogen, and vacancy. Okay. So how we express this kind of solution? That's the actual question. And also, if you look at the most of the ceramic solution, for example, you can have, for example, MgAl2O4 spinel solution. It looks like it's a stoichiometric actually phase, but internally there's the cation actually have the 2 different sites which it can enter. Okay. So for example, typically magnesium is going to the tetrahedral site, aluminum going to the octahedral site. So MgAl2O4 structure at the very low temperature. But when you increase temperature, the magnesium from tetrahedral site moving to the octahedral, it means aluminum actually going to the tetrahedral simultaneously. Okay, so we have the mixing of the magnesium cation and aluminum cation inside of tetrahedral and octahedral site. And also at the high temperature, even octahedral, some species in octahedral site is become empty, so it make vacancy as well. So even though it looks like stoichiometric phase, but sometimes those stoichiometric phase is internally have the more than 2 sublattice structure, and it have the kinds of the entropy, computation entropy is generated within this structure. Okay, and similarly we have this kind of pyroxene, we have M2 site, M1 site, and then you have 2 sublattice and etc. Okay, so all this kind of thing is more than 1 sublattice. So typically this kind of the solid metallic system or oxide system or even salt system, so whatever you have crystal structure, and typically we are using compound energy formalism, assuming the random distribution of atom in each sublattice. Okay, that's actually the assumption in the compound energy formalism, assuming that kind of random mixing of the species in the given sublattice, and then we create actually the solution. Okay, which have the more than 2 sublattice, and then in that case we have to use compound energy formalism. Okay, so for example, this one we have 1 sublattice, 2 sublattice. Okay, for example, this one, if you look at this one, potassium and magnesium going to the M2 site, it's a certain crystal, structure site, and then aluminum, magnesium going to a certain site in the given crystal structure, in the pyroxene structure, and that we call it M1 site. And silicon go to the B site, another silicon go to the A site, and then there's the oxygen around it, okay? So theoretically speaking, in this solution, we have 1, 2, 3, 4 sublattice, for example. Or even if you're including oxygen, we have 5 sublattice. However, real mixing is actually only happening in the 1 and 2 sublattice. Yeah? So real mixing is happening at 2 sublattice. So we don't have to make a 5 sublattice solution model. We need a 2 sublattice solution model. That's more than enough. Okay. So when we make Al2O3, Cr2O3, do you recall this one? We assume aluminum and chromium is mixing in the first sublattice, and oxygen is stay constant at the second sublattice. So in order to actually reproduce this kind, describe this kind of 2 sublattice solution theoretically, but we use the 1 sublattice random mixing model. Do you remember that? Because aluminum and chromium is mixing in the first sublattice only. So even though this looks like 5 sublattice we need, but in reality, in the modeling, we used only 2 sublattice model. Okay? And this is same thing, 2 sublattice model. So sublattice model is depending on the how many actual site you are actually having the actual mixing of the different species. That actually determines number of the sublattice. Okay. For example, in Paxage, we have our component formalism is expanded up to 3 sublattice model. 3 active mixing sublattice is actually described by the component formalism in the Paxage. Okay, and most of the time this is about 99%. This is enough, and very, very, very few cases when you have order disorder. It's very strange order disorder condition. You have more than 3 sublattice mixing. Okay, then unfortunately the current Paxage cannot actually reproduce those kind of solution. Okay, but as I told you, about 99% of the solid solution is covering within the solid sublattice. And most of them actually is 2 sublattice. Okay, so now let's assume this kind of solution. Okay, let's assume I have AD and BE kinds of the mixing. So this is one end member, this is another end member. So we have 2 components mixing as a solution, and A and the B is mixing in the first sublattice, and the number of the site for the first sublattice is P mole. Okay, in the given formula. And then D and the E is mixing in the second sublattice, and number of moles of the second sublattice is Q moles for the given formula. So given formula in this case is MP NQ kind of formula. Yeah. So in the given 1 mole of the formula, we have P moles of the first sublattice, Q moles of the second sublattice, and each sublattice is mixed by the AB and the DE. Then how we express Gibbs energy of this solution is like this. So Gibbs energy solution per mole of this formula is, we multiply, okay, so we assume that there's the AD kind of combination Gibbs energy, AE kind of combination Gibbs energy, BD kind of Gibbs energy, and BE kind of Gibbs energy. Do you understand what I mean? So in actually we have these 2 is mixing. So AD is existing there, if you look at this one. And then DE is existing too. And on top of that, we virtually assume there's the AE kind of the end member and also BD kind of end member as well. Because this is possible combination. Kind of matrix, yeah. First matrix and second matrix. So we just combine it first times second matrix, then we can have the 4 end member can be generated. Okay. Some of them is real end member, which we know the actually thermodynamic property. Some of them is virtual end member. Okay, we have to define the Gibbs energy in that way for those virtual end member. Okay, so anyway, so Gibbs energy of solution is defined first: GAD, GAE, GBD, GBE. Okay, and this is AD means APDQ, APEQ, BPDQ, and etc. Okay, so I just used only the term, but in fact, inside of actually this formula APDE, DQ. Okay. And then this Y is the special one. So Y we call it site fraction. So at the given site, so it's a first sublattice, first site. What's the mole fraction of A? That's YA. So between YA and YB. So YA plus YB equal to 1. Okay, each kind of mole fraction in the given lattice. Okay, so so basically I have YA moles and YB moles and YD moles and YE moles of species exist in each sublattice here. And so the amount of Gibbs energy I need for the AD is YA times YD. And then mole fraction, so site fraction of these two times Gibbs energy of APDQ. Okay. Similarly, YA, YE, and Gibbs energy of APEQ, and etc. Okay. So this makes sense, yeah. So this is just combination of the linear combination of the end member Gibbs energy, of the 4 end member Gibbs energy, we can create from this structure. And then we have now random mixing entropy. So inside of this one, we have random mixing entropy. Inside of this one, we have another random mixing entropy. And we assume that ideal mixing. So for mole of formula, we have P moles of the site A, and then A and B is mixing there. So P times RT, YA ln YA, YB ln YB. So this is per mole, and then we have P moles. So it's P is multiplied here. So this is ideal entropy of the first lattice, and this is ideal entropy term of the second lattice. Is it okay? So it's almost same as the one lattice model, but we just expand that into the multiply by 2. Okay, nothing other than that. And then we have excess parameter. So this excess parameter is again compound formalism, typically using the L parameter, the lattice type of the parameter. Okay, and when you actually define this L parameter, now the only thing you have to be careful is we cannot just assume, okay, what's the interaction of AB in the first lattice? So we have to assume that, okay, AB of the interaction, assuming second sublattice is only D, and AB interaction assuming second sublattice is only E, for example. And we have also BD or DE interaction parameter, LDE, assuming the first sublattice A site only, A species only, and DE with the first sublattice only B site. And then we have ABCD all together as excess parameter as well. So there's the little bit more complex actual formula for the L parameter, but it's actually almost same as the one sublattice model. The formula itself is one sublattice model. Is it okay? So compound formalism is still random mixing model, just expanding the random mixing model into the two sublattice. That's, I mean, you can assume in that way. Is that okay? So it is reasonably okay? Good. And then if you represent that actually in the 3-dimensional actually graph here, in the Gibbs energy actually graph here, it looks like this. So you have each end member Gibbs energy in the 4 corner. So we have in this actually axis, we have the increasing of the B amount, assuming D is constant. And in this side, we actually increasing the E amount, assuming A side and the B side, Is it okay? Something like that. And then we have the 4 actually end member Gibbs energy, each 4 of these. And then inside, I mean, this the 3-dimensional, this actually the curvature of this actually the solution is depending on the this and this with excess parameter. Okay, so in the compound energy formalism, the thermodynamic parameter here is end member Gibbs energy. This one, this one, this one, this one. This is one of the parameter. Okay, because you may have real AD Gibbs energy available in the literature. You may have real BE Gibbs energy available in the literature. However, you don't know this Gibbs energy and this Gibbs energy. So these two is already model parameter you can play. Okay, and then you have excess parameter. Okay, so you have a little bit more actually flexibility in the thermodynamic modeling. Okay, and a little bit complex because of that. Okay, now let's try to create the real solution then. Okay, so one of the things I want to actually try is this solution. So this is actually the paper I published like with my student, aluminum, chromium, magnesium ternary system. So I think I uploaded this actually the file already in the website, or I'll upload it today. And so if you look at it here, so let's look at a couple of them. So liquid solution, it's all, if you look at this shape, you can already see that this is MQM, modified quasi-chemical model. FCC, look at this one. We have two sublattice. However, second sublattice is only vacancy. It means it's the same as one sublattice model, theoretically. You can make two sublattice with the vacancy as a second sublattice always, or, I mean, theoretically, it's almost same as the one sublattice model. So here you say aluminum, chromium, and then semicolon and vacancy. So vacancy is always in the second sublattice. And then this aluminum chromium interaction in the first sublattice, that's L0 parameter, L1 parameter, and etc. You know. So this is same as, I mean, if you just forget about vacancy, it's the same as one sublattice, L parameter. Is okay? Similar thing, similar, and similar even this one. And then this one, even, you know, gamma L, low temperature gamma phase. So this is the name of the your phase, and this is actually the your sublattice. So aluminum 12, chromium 5, aluminum, chromium 9. So these have three sublattice. However, in reality, this is one sublattice model. Is okay? Because this is only mixing. Okay? This one is now real two sublattice model. So you have this one, you have the two sublattice mixing by the two different elements, and then third one and fourth one is one element, so it doesn't matter. Okay, so let's try to make this solution, or let's try to make this solution. Okay, this is again two sublattice. Yeah, let's try to make the last one, AlCl2 solution. Okay, AlCl2 solution. So now let me open my Eclipse file here. So aluminum chromium solution. Okay, let's look at it. Sorry, let's just make it a little bit more space. Okay, I want to make this solution, as you see, this one. And for this one, if you look at actually Gibbs energy expression, so G, AL, 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 CR, CR, AL, CR, CR, yeah? So 1, 2, 3, 4 Gibbs energy is defined. Can you see it? And then we have L parameter is defined, okay? So first thing we have to do is we have to define these 4 Gibbs energy, 4 and the member Gibbs energy, okay? And if you look at it, there's the sum value plus 3 times of the aluminum FCC, chromium BCC, aluminum FCC, chromium BCC, and etc. yeah? So we have to actually consider all this one. So that means when you take actually the Gibbs energy from the FT Light database, at least we have to take a Gibbs energy function of the aluminum FCC and chromium BCC first. And then we have to enter some additional actual value to create actually the new database. Is it okay? So let's start from the beginning. So let's say I'm not interested about this one. I'm making new solution, new. So for example, we can give the name, say, let's just go back to our edu version here. So aluminum chromium solution, I already made it. So AM solution, okay, aluminum chromium magnesium solution, okay, and then SLN database. So I made a new one, and then I'm going to add a now function, okay. So what function I need? So I have to go to my compound, and we are going to have aluminum and the chromium. So aluminum from the FT Light database and aluminum FCC page. Okay, I'll take this one and then push the mouse left button and then put it to my function. Okay, so I copy the aluminum FCC into my new function. Okay, and then chromium. Similarly, chromium BCC page. That was actually the one, so I copied it inside here. Okay, so this is done. I don't need any more because I need only FCC and the BCC chromium. Okay, and then we need some additional actual Gibbs energy. Now 1000 and then minus 14 something temperature and etc. Yeah, So we have to prepare something like this. So we can prepare 1 joule of Gibbs energy and 1 joule T Gibbs energy, for example. And then we can multiply with this factor later to create actually the function there, yeah? So go there and then add now, because this is special function, so we have to add function. And we say, okay, star, for example, how do I say? G of G and then 1 joule, for example, A joule, for example. G dash A joule, G underscore A joule. Okay. And then I define this one as 1 joule per mole here. Okay, so this is basically 1 joule. H, Gibbs energy equal to H298 plus integral Cp dt plus minus T of the Cp and dt and etc. So if I enter only this value with the maximum, for example, 10,000 or 5,000, okay, then I'm going to use this one as 1 joule Gibbs energy. Is it okay? And then going again, add another function and say G star G and then now BT joule. Okay, so say okay. So because I want to say A plus BT and BT, so in this case, T term, I want to add S298 as 1. And then this one again, 5,000. So look at this one. So what I did. So Gibbs energy, if you remember, Gibbs energy equal to H298 plus integral Cp dt from 298 to the certain temperature minus T of S298 plus integral Cp of the T dt. Am I right? So if I use this S, this B term as 1, Gibbs energy point of view, this is minus 1 T. Is it okay? This is minus 1 T. Am I right? G equal to H minus TS. So when I multiply 1 into the, when I give the 1 joule in the S298, this will be minus 1 T joule for the Gibbs energy. So if I say minus here, then it means it's 1 T Gibbs energy. Is it okay? Good? Okay. So now I can say, because we cannot put the actual T term inside of the end member Gibbs energy later. So that's why I prepare in this way. Okay. Now we don't need CP, of course. It's all 0. And now we go to the solution and to the mouse right click and add a solution. And you have to say that aluminum chromium AlCr2 solution, for example. That's the name of this solution. And we can add only maximum 5 characters here and then solve it. And then now if you click this one, we can have different solution here available. And then this third one, compound energy formalism, model 12 or model 20. Okay. And then from the beginning, you have to set how many sublattice you need. How many active sublattice you need. Okay, for the mixing. And if you have this one is magnetic like FCC, then you have to click the magnetic already, FCC, BCC or something. If it is non-magnetic one, you don't have to worry about it. Okay, so I need 2 sublattice, lead sublattice, or whatever. So 2 sublattice in this case. And say okay. Okay. And now I'll just click one more and then click. So now I have A site and B site. 2 sublattice, yeah. So sorry. So this is my first site and this is my second site. So how many end member how many species I have? 2 species and 2 species. So here I say species 2. Okay. And then B sublattice species number 2. Okay. And then here, this is actually also important. So number of moles of the site per formula. Okay. So this is 1. First sublattice is 1 mole. Second sublattice is 2 moles. So this is 1. And however, this one is 2 moles. Okay. And then now, what's the element? I have aluminum. You don't have to actually add this formula because it's optional. You don't have to worry about it. And this is now chromium. Okay. Again, same thing. This is aluminum, and this is chromium. Okay. And then now we have to define end member. And the member was, as I show you, so this one, aluminum, aluminum end member, chromium, chromium, the aluminum, chromium end member, this one. Okay. So let's try to create it. So let's just move this one a little bit. So we can actually have time. We can have room to I'm sorry, it's not moving easily. So like this. So now aluminum and then control key, and then aluminum, push the control key and do the mouse right click. Then you can add aluminum and the member. Aluminum, aluminum and the member. So this one, as you see, one side, two side. A is 1, so aluminum A is 1, chromium is B2. So now you have to give the real formula. This is important. You have to give the exact formula. So aluminum 1, aluminum 2, yeah? Or you can say Al3 if you like. So you can do it in this way, or you can do simply Al1, Al2, or you can even say, okay, Al3, doesn't matter. So this is the actual your element, actually the elemental, actually the formula you have to enter for this specific end member. Okay. So if you like aluminum, again, aluminum 2. This is also okay. 1, 2. Okay. Now Gibbs energy function. So here, so this was the one I want to enter. Yeah. So this one. Now 1, 2, 3, 4. 10,000 joule plus 3 times of Gibbs energy of aluminum FCC. Okay. So we say that, okay, here, aluminum FCC, aluminum star FCC underscore A1 plus now 10,000 times G underscore AJ. Is it okay? Because AJ was the 1 joule. Okay. So 10,000 times, that's actually the 1 joule. So that's exactly the same as this one. Okay. We can do the similar thing now. So, sorry. So sharp, sorry. You have to say sharp. Okay. Is it okay? Because there's no heading for this one. And then now second one, sorry. Now chromium, 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 chromium. So the mouse right click, do the same thing. So this is chromium, chromium 2. And then this Gibbs energy is given as this one again. 3 times, I'm sorry, I should actually make 3 times of chromium, sharp, BCC, A2, plus 10,000 times G, so sharp G underscore AJ. Is it okay? And the first one, let me go there again. So this is 3 times, yeah? 3 times of the aluminum. Sorry. So this was 3 times of aluminum FCC, 3 times of BCC. So this one and this one. That's done. Now, next one, aluminum, chromium, chromium, aluminum. Aluminum, chromium first. Aluminum, and then chromium. And then go here. This is aluminum 1, chromium 2, yeah? So 1, 2 formula. Okay. And this gives energy. Aluminum 1, chromium 2. This is actually expression. So you have to say that. Okay. So aluminum sharp G FCC A1 plus 2 times chromium sharp BCC B2 A2 plus you have this one minus 3 6594.81 and then minus 14.91 so sorry, I have to do this one sharp so G of AJ minus 14 star 91 times now sharp G DJ DJ. Is it okay? Is it okay? So this one was the constant term, so joule, and this is the T, 1T times minus 14.91. So minus 14.91 times G of BJ. So this one, BJ, was the 1T term, yeah? So I have to do it in this way. Okay, and then we can do the third one. Now chromium, I'm sorry. So what was wrong? BTJ, sorry. Okay, BTJ. Okay, the name was different. So now third one is chromium aluminum. And then to the mouse right click and then do it again. So this is chromium aluminum 2. And then you have to now enter this one, yeah? So now this is 2 times of aluminum sharp G sharp FCC for A1 plus chromium BCC A2 plus 5233.31 times sharp G for AJ and plus 16.84 times sharp G of BTJ. Is it okay? So this is how we enter all the Gibbs energy. So each of this one. Okay. So this is very simple. I mean, we just add some additional one. This is same thing. And this one, even we say A plus BT and A plus BT. Okay. So this is all the parameter we optimize basically. So when you do the thermodynamic modeling, you have to optimize all this one, this one, this one, this one, this one. Okay. And how we find this one? Case by case. Okay. So sometimes it's already predetermined by some other, solid solution solid solution with connecting with this one to the another one. So for example, this is aluminum chromium 2. Let's assume that aluminum, and then in second sublattice we have chromium and the manganese together. Then aluminum manganese, we have the similar kind of shape, and then somebody already did the modeling in that aluminum manganese. Then aluminum should be taken from there. Okay. So we have to actually, this one is already picked from that previous work, okay? And so in some cases, we actually pick in order to have the one, consistent database, sometimes we have to use this kind of predetermined value from the other binary system or the other part of the solid solution, okay? So it's making the binary is simple, but when you make actually the multi-component system, you have to consider all this kind of the connecting point. And then because of that, you might have some limitation in terms of modeling. Okay. So that's actually the one thing you have to be actually careful when you create a more than ternary system. Okay, now the last one is this one, aluminum chromium, now L parameter. So look at this one. So this is a little bit strange form. So if you look at this, so this one, so there's also some other cases like this too, yeah. So this means aluminum, chromium, and the star, and dot and the star. So it means we are considering aluminum, chromium interaction parameter in the first lattice, assuming the second one is aluminum, and that's this value. Also, when it's chromium, we are using same value. So whatever second actual sublattice is, we consider that as the same value. That's what it means. Okay, and depending on the actual people, sometimes they are using aluminum, chromium dot aluminum, and then equal aluminum, chromium dot chromium equal, and this value. So it's specifically more telling you actually what's the actual real number here too, more actually clearly. And sometimes if you're actually showing in this one, you have to look at actually the expression inside of the the paper, but typically it explained that, okay, this assumes that regardless of the second sublattice species, the first sublattice interaction aluminum chromium is this value. Okay. So when you have, for example, aluminum chromium and then aluminum, for example, and then now we can add the interaction parameter, Bragg-Williams, Radley-Kister, and then here you see aluminum chromium AB, and then second sublattice was the aluminum. Yeah. So aluminum is not showing up here, and that L0 parameter is basically -8922.6. Okay. Similarly, for aluminum chromium without this one, aluminum chromium and the chromium, aluminum chromium and the chromium, and to the Bragg-Williams Radley-Kister one again, and this value is same as the first one. So this is again -89.22.60. Okay. So that is aluminum or chromium for the second sublattice. We are adding same number. Okay, that's what it means. And then second one. Now first sublattice I don't care. So it means I have one of the first sublattice and two second sublattice, and then to the mouse right click again, and then Radley-Kister term, and this is -38108.20. Okay, and then again same thing, chromium and aluminum chromium, and similarly we can go here, say -38108.20. Okay, so this is done, and then you can save it. Then this is AlCr2 solid solution Gibbs energy using the two sublattice model. Okay, so similarly you can create all the other solid solution if you like. Okay, it looks like complex, but I mean if you understand actually the sequence here, it's not very complex. It's actually very simple. It may be more simpler than the quasi-chemical model. Okay.